So database people will tell you that I will not call something a database unless it is huge. So if your data fits in memory, then it's probably not a database. So it has to be a massive piece of data. What massive means changes from year to year. So now it's like terabytes, petabytes, and whatever massive word that's available today. How many of you are taking a course from Chris Carruthers? What's the word he's using?
Petabytes.
Peta? No, we should probably have peta. Exa? Exa, there you go. Lots and lots of data. All right. So if it fits in memory, we are not so excited. What that means is that a lot of the things that you learned up until now, and correct me if I'm wrong, have to do with organizing data efficiently in memory, right? So, you learned a lot. Data structure is about organizing things in memory. But when we are looking at storing data in disk, some things changed. And the world is kind of interesting because the things that change are also changing as we speak. So changing in ways that, are going to affect how you do this over the years. So over your lifetime, and you are in the business, if you're doing things that have to do with databases, you will need to adapt to some of the changes that are coming. Winter's coming. I'm waiting. Okay, so this class starts with this very important word. Disks are, what are disks? Slow. Okay, so this is the most important things to remember. So your data is stored on disk. So how many of you must have all taken computer organization, right? Okay, so you learned that, there is a hierarchy of how information is stored. You probably know more about the common architecture, modern architectures than I am. But generally speaking, your computer is basically kind of has these two main parts. One is disk, and the other one is memory. So memory is basically volatile. When you turn off your computer, whatever is in memory is lost. Okay, you probably never turn off your computer anymore. But let's say if power goes off and your disk fails or whatever, and disk, whatever is on disk is not volatile. You with me so far? Okay. So whatever data that is dear to you, you store on disk because it's the non-volatile thing. So this is what we call stable versus volatile. And whatever you need to do, whatever data you need to read or write, you bring from disk to memory. Okay? And whenever you want to make it permanent, you write to disk. But everything you do is, of course, done in memory. Memory is where you do all your processing. If you're going to crunch numbers, you do that. If you're going to do a select from where, you do that in memory. But ultimately, the data is back stored on disk. And the thing is that your database is so large that it's not going to really fit all at once in memory, right? So if you're asking a query, it's not like it's going to read all the table into memory first and then answer your query, because often that's not possible. That is just too huge. You might say that most of the data you use is not true, but think about just this database, this class. This class's database. That what we did have was, a database that was medium-sized, but hundreds of people were accessing it at the same time, right? And they were all accessing a different part, so whatever they need probably did not fit in memory. So basically the idea is that you basically need a way to take data in from disk, bring it to memory, do what you need, and write it back. So this is the most important thing to keep in mind for everything that we talk about. So the thing that we really are going to discuss is what does it take to read data from disk? And the fact that disks, reading information from disk to memory, is much, much slower compared to something you can do in memory. Okay? So how much does it take to read a page in memory? How many, is it in milliseconds? To read content of a, let's say, 8K page that's already in memory. How much does it take, you think? Let's say a few milliseconds, maybe 2 milliseconds per, let's say, 1K. Whereas reading that page from disk to memory may actually take you 8 megabits per second. 8 megabits. 8 milliseconds, right? Could be orders of magnitude larger. So why that is the case, we are going to talk about that first. So we are going to talk about what is a disk, and what does it take to actually read data from disk. And so basically when we talk about databases, we always kind of talk about disks. And when we say disks, we generally mean magnetic hard disks. Right? And it looks like this. Let's see. This is like, you know, the Terminator T100. This is actually the first the IBM you know, laptop that, you know, people used to get, like the, you know, what is the T, yours is now T what? T430. This is T20, right? So this is the earliest model of Terminator. So so basically, you know, it's a all right, I don't know how to do this. There we go. I have to put it on here. So basically, it is a physical medium. It actually involves moving parts. You have this surface, the platter, right? It has to start spinning for you to be able to read things. Data is written on this in concentric circles, like this. And to be able to read from a certain part, let's say here, you have to have this head move to there. This actually used to be like this. Move to the right place while this is spinning. And then you have to wait for the right location to come in. And then this head can start moving data out as soon as it's in the right location. Okay? And this one, you cannot see this, has exactly 2 platters. Can you see the 2 platters here? I have 1 and 2. But the newer and newer hard disks actually have, you know, multiple platters. So, so let's see, I have a picture here. So basically you have a hard disk have multiple platters. And generally you can read and write on both sides of a single platter. And each one is called a surface, right? So you have 4 platters, means you have 8 surfaces. And you write the data on concentric circles. What they do is they change the density so that the density it's denser in here and in here. So even though this is a smaller circle that actually has same amount of data as this one, just to make the software part easier. And the one circle like this is called a track. So on a given surface, you have different tracks. And then given a track, you generally take the track and you divide it into logical units. They're actually physical units separated by spaces that do not contain any data. So these physical units, we call them sectors. And generally, you know, the sector is really the smallest unit you can read, because there is no subdivision of sector. Sector is the only thing that the head can tell is from moving one sector to another. But generally, you have a logical unit called a page that is multiple consecutive sectors. So, your page may be, 1K or 8K, which may map to 4 sectors. So, this page may or may not be the same size as a sector, but, generally, let's say it's multiple sectors. And, yes? I'm sorry? A page can span multiple tracks, but whole units of tracks. Oh, no, I'm sorry. A page cannot, it has to be on a single track. Yeah. It's basically kind of grouping, like a group by of a single track. So basically, to be able to read a page, first the disk has to start spinning if it is not yet spinning, which is a physical operation, right? So, and then as it starts to spin, the head tries to move to the right track, right? So so basically, the point of the head moving is kind of a physical motion that is going to be difficult. So that is going to be called the seek time. Okay. So basically going to the right track. Then, as you move to the right track, you have to wait for the disk to spin to the right location. So you have to wait for the right sector to come in the track, right? So seeking the track. Then you have to wait for the rotation to complete. So this is called rotational latency, okay, where you're seeking right sector. Now once you're at the correct seek time and seek correct track and sector, you can start reading from there. Then you basically can transfer data. Okay. So basically, anytime I teach this class, I basically go back and see what has happened in the world of disks, right? Have things have changed? I can tell you that in the last decade or so, the disks have not gotten any faster. They have gotten denser, but the rotation is the same. What is the physical limit for rotation speed? 10,000 RPM, but what limits it? And? Yeah, yes. So what does this generate? Heat, right? So heat, power consumption, big problem, right? And so people, instead of trying to make it run faster, turn faster, they have been trying to make it denser and faster. But that's not really going anywhere that that fast either. So the capacity is increasing, but speeds are roughly not changing because you're not really changing the seek time. The seek time is a physical action, right? So the arm has to move, and so generally speaking, the most of the disks that we see are about 7,200 rounds per minute. Or RPM. Maybe today you see more of disks of this. In the past that they were fewer, but it still is not getting much faster. And the seek and rotational latency doesn't change too much. But since it's denser, you may be able to read a little bit more. And so your page sizes may increase. So one of the nice things, though, once you move to a certain track, you can actually read from all the surfaces. Generally, there are multiple arms, so you can read, that track from many, many surfaces at the same time, right? So if you do one seek, you can actually read multiple things all at once. So let's see some example. For example, this is a reasonable, reasonable example. So let's look at a disk that has 16 surfaces, 2 to the 16 tracks per surface, and 2 to the 8 sectors per track, and 2 to the 12 bytes per sector. Okay. So this is a decent sized disk. So each sector is 2 to 12 bytes, which is 4 kilobytes. Right? 2 to 10 is kilo, right? Everybody's looking at me. All right. So it's like 4 kilobytes per sector. So given that there are 2 to the 8 sectors in a single track, so you have 2 to the 8 times 2 to the 12 means 2 to the 20 bytes per track on a single surface. So 2 to the 20 is what? Mega? The megabyte? Unity? All right. Come on, ComSci students. All right. So, given that you have 2 to the 16 tracks per surface, okay, so you have about 2 to the 36, 2 to the 36 bytes per surface. Okay. And now suppose you have 16 surfaces, meaning 8 platters. Okay. So 16 is 2 to the 4 times 2 to the 36, which is 2 to the 40 bytes in this disk. And 2 to the 40 is terabyte. All right, we did that. Okay, so this is a reasonable terabyte disk. Which is, I understand we are getting, 1 terabyte, 4 terabyte, 8 terabyte, but, it's kind of roughly the order of stuff we deal with. This is a reasonable way of thinking about how it drops. So if you want to find a certain sector, right, you have to tell me the address of that sector. So the address of that sector would mean that you have to tell me, so we will call this the physical address. You will have to tell me the surface number. Then you have to tell me the track number. And then you will have to tell me the sector number. Okay? And you can tell me how long this address is going to be, right? To be able to address this, you have 4 bits for surface. You have 8 bits for track, and then you have, right? Yes. Then you have 16 for track, and then 8 bits for the location, right? So this is a physical address of really locating a single piece of data on this, what the physical address is. So how long does it take to read that? So think about this. There's a very simple thing about 7 to 200 rounds per minute, right? So that generally means that one turn takes about 8.3 milliseconds, right? Can you do that calculation? So if you have 1 minute is 60,000 milliseconds divided by 7 to 200, that comes to be like 8.3. So one round trip, one round rotation is about 8.3 milliseconds, okay? You can compute that because that's the same as 60,000 milliseconds in a minute divided by 7 to 200. It comes to be 8.33. Okay? Now the arm's speed of coming from, whatever it was before to there, generally depends on how fast your disk is. So so the seek time is generally between 0 to 17 milliseconds in regular disks. So now this is kind of, if you've taken probability, you can tell how this is computed. Generally, in the worst case, you're in the wrong end of the disk, and you have to move all the way to the end. That will take 17 milliseconds, right? But often you are somewhere in the middle, and you have to go, roughly half of that. So you generally have to pay about a third of this cost. So we are going to say that the seek time is about 6.46 milliseconds, right? So we are going to generally assume seek time is 4.3 milliseconds. Is that what I said? 6.46, so 6.46, right? And then the rotation will depend on how many sectors you're going to read, right? If you're going to read one sector is about 1/12 of the rotation, right? 1/212 of the rotation. 1/2 of the rotation. To the date. Here we go. There we go. Now I did it. Okay. So one sector is 1/2 of a rotation. So that would be, 8.3 divided by 2^8, whichever that is. Okay. All right, this is very low level, but we're going to go up slowly. Okay, so let's do a simple calculation. Suppose I want to read 10 pages. Okay, let's say it's the same as 10 sectors of data. Okay. Well, your cost of how much this is going to take really will depend on where this data is stored. So let's say that all these 10 sectors are actually consecutive. Okay? And actually make this even better, let's say 16. Okay? So let's say, suppose 16 pages are consecutive on a single track of the disk. So to be able to read these 16 pages, I need to first move the head seek to the right track, right? So we are saying that's about 6.4 milliseconds. So I have to first do a seek time, which is 6.46. Then I'm going to wait for the this to spin to the right location. So that's maximum 8.3 milliseconds, right? One spin. But let's say in the average, I wait roughly half a spin, right? So I'm going to say in the average, my rotational latency is about half of max. So this is going to be 8.3 divided by 2. Then I'm going to read all the 16 pages all at once after this. Read 16 pages. So then that's going to be reading a single page or single sector was 2^8 8.3 divided by 2 to the 8. And then I'm going to do this for 16 times, which is 2 to the 4, right? So if you were to compute this, this is 6, so 4, that's 10, 10.6, so it's roughly 10.6 milliseconds. This is generally negligible, right? So 8.3 divided by 16 is 0.5, so this is probably like 11. Am I close enough? Right. So 11 milliseconds to read 10 pages of data. And each page was about, 4 kilobytes. So, I read quite a bit of data. And it took me 11 milliseconds, which is, again, for what we are used to, is a lot of time, right? 11 milliseconds is so much more than what it's going to take to read this once they're in memory. This kind of search is called a sequential scan. So we are actually accessing pages sequentially on disk. If it was not really sequential on the same track, but they were all on the same cylinder, then this would still not be so bad, because in one spin I can read everything, right? In the worst case, it's 8 milliseconds. Okay? What is the worst possible case? Okay? What's the worst case of this? Yes? It is like they are in completely different locations, right?
I mean, worst case would be that each one is in the same relative location on a separate track.
I see, like you have to wait one for each one. That's true, that's even worse than what I was thinking. All right, well, I'm not going to do that, but that sounds really bad. Okay, so like you've gone as far as you can. So not only that they are in different tracks, but every time you finish one, when you go to the other one, you still have to wait for a full spin. Seems pretty rough. I'm not going to do as bad, but that's technically also possible. So that's our second scenario. Suppose all 16 pages are on different tracks. All right, that sounds pretty rough, right? So what does that mean? That means for every single page, I'm going to seek once, wait for rotational latency, then read, right? So for 16 times, I'm going to seek plus do a rotational latency plus transfer time. But transfer time is going to be so small that I can actually disregard. 8.3 divided by 2 to the 8 is pretty small. So this is the same as saying that is 16 times 6.46 plus 4.3. So that's 10.7 times 16, which is, it's greater than, so this is greater than 160, right? Right? Do you see the difference? 11 milliseconds is already a lot. 160 milliseconds is crazy, right? So 160 milliseconds just to read 16 pages. What this is called random access. Okay, so this is in fact the main property of magnetic disks that we are going to really care about. That there is such a massive difference between sequential access and random access. So there is a thing in your vocabulary that your computer slows down when you have this fragmentation, right? That all that means is that now you have a lot more random access, right? Just to read a single document, it is now stored in many places, so you do lots of random access. right? Except for those of you who have what kind of disks? Solid state, right? So that's where the difference lies, okay? So in fact, this is not the only technology. This is the most common technology, and this is the cheapest technology, okay? So if you're going to have petabytes or exabytes or whatever is after exabyte, you are not going to store that on solid state because solid state is very expensive still, right? But hybrid solutions exist. But the point with solid state is that it doesn't have this distinction between sequential access and random access. It only has access. Because data is actually stored on chips that basically don't have any moving parts, right? So solid state disks versus magnetic disks. Okay. And you have to remember that disk is with a K, not with a C. That's the music disks. Okay. So solid state has no moving parts, whereas you have physical movement. So as a result, solid states are, they don't really consume as much power, so use less power, more power, okay, obviously. And solid states are generally faster than hard disk, but a hard disk on a high of sequential access does quite well. But when it is random access, it does horrible, right? So when you're comparing a hard disk speed, you have to look at what it means, right? So comparing sequential access versus random access. So it's generally faster. So I'm gonna say somewhat fast only for sequential access. Okay, but it's not like solid state is not. How many of you have solid state on your computers? Right, not everybody, right? Because it's still not as common. There are two things. Their reliability is not higher. Their reliability is slightly lower still than magnetic disk because magnetic disks have been around. Okay, when they first came out, the reliability was actually a big deal. I looked. Don't give me that look. I looked. It's slightly lower. So they are not more reliable, but they are certainly more expensive. People accept this? Okay? All right. So Jim does not agree about reliability. Anytime I say something about solid state, people have issues. So, all right. It's okay. We'll disagree. I searched it just yesterday. But depending on our sources, there are some issues with reliability. Okay? When I first got it, people were really down. Now it's not, but mean time to failure was 15 on one and 20 in the other, so it's like they are similar, but let's say similar reliability just to make Jim happy. All right, similar reliability, but much more expensive. So currently, when it first started, it was much more expensive, but now that it's been going down, so as a result, now it's about 2 to 1. But it still is more expensive. And generally, the max capacity is for these ones is smaller. You can get an easily 8 terabyte hard disk, but you may not find that many 8 terabyte solid state disks. You agree? Do you agree? Max capacity is smaller in general? All right. Well, that's okay. So this is higher. Okay. So what does that all mean? Okay. So I'm going to talk about magnetic disks because really a lot of the database theory is based on this. Okay. And some of that is not going to be valid if time has passed and now solid state is dirt cheap and that's what everybody is using. in that case, you have to revisit the database theory and see which database is that, right? But generally speaking, your solution is a mix of these. And one of the things that databases care most about is that when you're storing data, storing it consecutively on disk is important. It's not always possible, but as much as possible. So if you left it to the operating system to store your data wherever it wishes, this would not be very good, right? Because you are not guaranteed to have this property. The nice thing about database is it knows which data pages are going to be accessed at the same time. Like all the tuples for a table are often accessed at the same time. So what it will try to do is it will try to allocate multiple blocks at a time that are consecutive, and then put your tuples in there. Okay? So one of the reasons why you want a database as opposed to your own, home-cooked data storage system is that it does maintain this consecutive storage so that you can do more sequential access, less random access. So this is one of the second things like we want to remember from today. So we said disks are slow, okay, and sequential access good. Okay. So now, if disks are slow, and I want to make my database faster, what is the one foolproof way to make it faster? Right? You can write better queries, you can have better data model, but there is something that always works.
That's data.
I guess that does always work. What if I cannot have less data? You decided all your current data is important. Buy more hardware. Yes, that works. Right? Buy more hardware. Buy more memory. Buy more disks. There's a name for that. We call that RAID. Bane of my existence. Okay, so this was actually a real research paper that was my best paper, and then became such an important thing in industry because it's a very simple idea. So since your hard disks are cheap to buy, you can buy many of them, and if you buy many of them, you can make things faster. How? Well, RAID means redundant arrays of inexpensive disks. Okay. It does not say redundant arrays of solid-state disks. So RAID is basically this methodology where you can use multiple disks to store the same data, but you can actually improve a number of things. There are two things you care about. One is read-write speed. The second one is redundancy. Redundancy means that even if some disks fail, maybe you may or may not lose data. How many of you use RAID? Okay, so it's not yet so common that it comes with your laptop, but it does come with a lot of desktops. So the idea is that RAID is something you can implement totally on software level and totally on a hardware level, but hardware level will require some controller that you buy, which is expensive. And any system admin that you use will want one or the other and will hate you if you choose the other one. And you will continuously hear how the other one's so bad. And you will continue to hear it every single day that you have a system that uses software RAID if they like hardware RAID. So the idea is very simple, but I'll give you a few examples. Maybe let's give a short break and then we'll continue. And I know that a lot of you have an exam right after this, so I will try to give you some time so you can kind of get fresh air. And I really feel like it's abuse to have people take exam in this room, so I'm very sorry that that's what happened last time too. So let's give a 5-minute break and I'll start from here.